All right. This is okay. This will be fun, I think. Um, yeah. Okay, so TLDR, like, what are we even doing here is the real question. So I don't know. Anyways, maybe this it's like a little bit of a story time. So, um, for a long time, I guess a few years ago now, but kind of really became more real. Um, One of the things I got interested in was this idea of interactive theorem proving. So, what's the main goal? Essentially, like, you know, there's a bunch of questions. Was like, how do you know that a math proof is true? And it's a really philosophical question because yes, like what is the point? Math has like some axioms, right? And from those axioms, you can derive statements and apply different axioms to different statements. For example, you can add things to two sides of an equation or whatever. And in doing so, you get new statements, right? And if you have followed the rules of the game, namely you have applied kind of the rules of equivalence, the rules of and, the rules of or, and the axioms, at the end of the day, you should get statements which are true with respect to that system. So, like, you know, a natural thing one might want to do is like, prove 1 + 1 = 2. This has a bunch of questions about like what it means, what one means, what two means, whatever. But the point is like you can start with some definitions, right? Like the definition of one and the definition of two, for example, which I think hopefully maybe that'll be one of the goals is we'll prove 1 + 1 = 2, and apply these definitions and apply these kind of formal rules in this game to get the result that like indeed 1 + 1 = 2. So okay, so like I guess this like begs the question. This begs two questions. Number one is like, what is a mathematical proof? And then number two is like, what does it mean to construct a system of proofs inside of like a programming language, which again is a little bit of a weird notion. Like we have, okay, so let's start with like the idea of a proof. So funnily enough, actually, this is very old school. So the original reason computers were constructed was not to perform arbitrary computations. I guess like Babbage engine was, but like the idea of general computers in the sense of like Turing actually was as like this idea of like an automated theorem prover. So again, like let's think back as to what math is. Math is like a set of rules that one can apply, right? And in doing so, like receive correct statements, right? So we have, the statement that is like, whatever, is the Riemann hypothesis true? And if it is true, there should exist some, from the axioms of math, there should exist some set of rules by which we can like take these axioms and build them up to construct, the proof of the Riemann hypothesis. In Turing's vision, this is like a mechanical process, actually in Gödel's vision as well, right? Like the mechanical process is like, look, there are a finite number of rules. We can apply them a finite number of times to get like a finite proof. So naturally, we like have a machine, right? Which is I believe Turing's mind is kind of this like abstract magical machine that is like the perfect mathematician that can like derive true statements from like this like set of axioms, right? So by applying these rules in like a consistent way, you could imagine just like putting stuff together, and at some point or another, one of the millions of proofs that come out is like, cool, a proof of the Riemann hypothesis. So in that sense, right, like actually we've kind of gone backwards. we started with computers as kind of like the idealized mathematician, which performs a like set of steps and in doing so receives like a true output. But now we think of computers as like kind of the opposite. Computers are just like very, very like good and very, very fast and smart calculators. But the point is like this is kind of a weird philosophical distinction that didn't really exist in like the advent of these like idealized computers, simply because of the fact that like it was very obvious that proofs, calculations, and all of the stuff was kind of the same thing. So, okay, so that's the conception of like computers and proofs, and hence why it's like not so weird to see like a set of computations as like in some sense a proof that something has been done correctly. That's fine. Now the question is, how the hell do we actually formalize this, right? Like, what does it mean to like run a proof, right? What does it mean for a like program to construct a proof or whatever? This is where it gets a little bit weird, and so we're going to use one particular version of it because, okay, so cool. So we have this like weird history of, you know, like computing essentially being in a sense like this idealized notion of like a mathematician or a calculator who like performs all of these steps. Then there's a secondary point here, which is, okay, cool, like that's a cool like idea, but that doesn't actually tell you how, you know, there's one thing, which is to calculate what 2 + 2 is, in other words 2 + 2 = 4 or whatever, and there's another thing to kind of prove from axioms that 2 + 2 = 4, right, and verify that in some sense, right? Like there's some notion in which these two things are kind of equivalent because, again, we're applying some fixed set of rules to get 2 + 2 = 4, and similarly, if you apply similar sets of rules, you can use that to prove 2 + 2 = 4. But now there's a question of like, how do we kind of formalize that, right? Like, what does it mean to take, you know, what does it mean for a program to like be put into a computer and for the computer to verify it? So here's where we're gonna like, this is what Lean does. This is what, you know, if you've heard of all the stuff around formal verification or automated theorem proving or interactive theorem proving or all this stuff, this is like the core of that, right? So there's many ways of formalizing mathematical proofs, right? When somebody writes a mathematical proof in like a paper, that proof is in some sense generally easy to read, easy to know whether it's true or not, but it's actually not like what one might actively call a formal proof. The reason it's not is because when you write something like, we take a linear combination of a bunch of things, right, you're actually like, there's a bunch of stuff that is like, needs to be parsed inside of that statement, right? Number one is, what are you taking a linear combination of with respect to what space and all of this stuff? Okay, so what we're gonna do, right, like, so this is like what's on like standard, you know, mathematics papers, but what really happens kind of a ways down is you need to kind of unpack all of the symbols that exist in like a theorem, right, and give like very precise notions to each of them such that like recursively these things can get mapped down to the axioms and then built back up, right, such that like, okay, cool, yeah, we have a finite field is like a thing that exists, that we know exists, but, you know, how do we know it exists? Well, you can build one by taking, you know, the integers modulo p and then proving that addition works and multiplication works and there's inverses and all this stuff like makes sense. Okay, so when we write a theorem in like normal math, right, we like of course know that this is all true simply because of the fact that we've kind of built this tower of abstractions, right? And, you know, once you've constructed a field once in your life, you never have to think about constructing the field ever again. The problem, of course, is like in a very like strong sense, a theorem or a proof of a theorem actually requires that like all of these constructions make sense at all points. So in some sense, we have to have this like way of doing multiple things. Number one is, what does it mean to write a like formal statement that has all of the things that that statement depends on, right, included in that statement? And number two is, what does it mean to verify that statement, right? Like if I have a proof of a statement, first of all, what even is a proof of a statement, right? And two is like, what does it mean for that proof to check? What does it mean for that proof to like compile or like verify? In like the most naive sense of the word, you can think of math as being like statements, right? And rules which you can apply to those statements. And in doing so, you change them. So one rule, for example, is like the reflexive definition of equality, right? So if you have like some object A, right, then necessarily A equals A, because that's like one of the definitions of equality. Another possibility is, okay, let's say I have a hypothesis that A equals B and B equals C. These are like statements. These are like strings that we have in our heads. And one of the things you can apply is like the definition of equality that says like equality is also transitive. In other words, it is like a rewrite rule, right? If I say A equals B and I similarly say B equals C, then necessarily what that means is that I can take the symbol B in these expressions and replace them with either C or A, right? Which in turn means that like A equals C or C equals A in the case of this, like, also like equality also satisfies this idea that like you can swap the order of the arguments and it's still true. Okay, so cool. So we've talked a lot about like, okay, yeah, we can think of kind of, statements as strings and axioms or rules as things you can apply to those strings, but that's pretty messy, right? Because, for example, we can write a lot of nonsense strings, right? Like I can say like A equals a tiger or something, and that's very annoying, right? Because in some sense, like a tiger and like A like may be of different types, right? I could say like the statement like 2 equals the empty set is like in some sense a statement that like can be made to make sense, but it is very weird to compare two things that are kind of like distinct objects that are unreasonably different, right? And so this is kind of where we start doing fancier things, and this is where we're going to get to like how we're going to formalize this specifically in Julia. So of course, like as programmers, there's this notion of a thing called a type, right? So like the reason why the statement, when I say like 2 equals like the empty set doesn't actually make that much sense is because, yes, correct, Lucas, this is true, right? Like logicians like disappear. Like immediately they just like explode into a fine dust, never to be seen again. So, okay, the point is like we have, 2 has a type, right? Like, so the notion of 2 is going to be like a natural number. 2 might have other types if it's not a natural number, but for now, let's take it as a natural number. And the empty set also has a different type, right? Which is namely like a type of a set, right? Or as we'll see, these things are terms. And so then the idea that they're incomparable is simply because like, look, in our heads, like the set, empty set, and the 2 have like different types. And therefore they're like the notion of comparing between these types, unless it is well defined elsewhere, is like not a useful statement. Right. And indeed, like this idea is going to hold the key to how we're going to actually like embed a lean-like or, whatever, so formal verification / interactive theorem prover inside of the type system of Julia. So I guess I kind of hinted at this a little bit ago. I tweeted something about it. This is going to be like rebuilding that from scratch in a slightly nicer way. But it'll be fun, hopefully. So, okay, so very quickly, what's going to be the high-level architecture? Let me just very quickly start a new package. So it's, I don't know, let's call this interactive proving or something. Okay. I'm going to open this. Okay. So finally, let's actually talk about how we can. So we talked about like statements. We talked about things that like make sense. How do we actually encode proofs, right? Like we've gone through this whole rant. Like let's go back. So what fundamentally is a proof? Or before that, what is a statement, right? Like when we say like a thing is true, that's a claim about a statement. And what we're going to use this very beautiful thing called the Curry-Howard correspondence to show, like, to essentially build these things up nicely. But in our construction, a statement will be a type. I'll be very concrete on what that means in a second. But a statement will be a type that is who essentially the type describes that statement. So one version of it is like 0 equals 0, will be a statement that we can make. And that statement has a type, right? Or sorry, that statement is the type, which is going to be a structure called equality, which is going to take two types of terms, namely one of which is 0 and the other one of which is 0. Okay, so again, this is a bit weird, but like bear with me for now. The point is like that is a hypothesis, that is a statement that we can make. And one says a statement is true if it is possible to construct an object of that type. So, for example, the statement there exists 0 is true because essentially, like by definition, we are going to take that there exists some object called 0, and we can construct that object, right? Which immediately implies that like the statement there exists 0 is vacuously true, or like trivially true, because we can construct the object called 0. Okay. The observation that like Curry-Howard does essentially is this idea that, okay, statements are hypotheses, or statements are types, right? And rules are functions. So, for example, a rule that is true, like I said before, is this idea that if you have an object A, right, that object always equals itself. That is a rule about equality. And that will be a function. So we can think of a rule, for example, the rule that says for any object A equals A as a function. That function will take a construction of this object A and will return an object of type A equals A. So in other words, it gives you the hypothesis that says A equals A, and it also gives you a like constructed, like it constructs that object, right? And in doing so, it tells you that this thing is true. That is how Lean operates. So in Lean, very similar to here, you know, a hypothesis or a theorem is a type, and a theorem proof is a set of functions applied to one another that result in that type. If you're a constructivist, this is just a total sidebar. If you're a constructivist, that type is like that proof is actually like the proof to construct that object, right? So specifically, like in constructing an object, you have revealed its truthiness, right? And this is like the notion of constructivism that we care about. If you are kind of a classical mathematician, you can think of this not as a construction, but you can think of it as kind of like an aid that says, you know, we have a hypothesis of type, and like if there exists some object of the type, then necessarily all of the like standard rules of math checked out, and therefore we are good, right? So this is kind of a first point of philosophical divide between these two camps. Okay, so in that idea, right, like this idea of cool, a rule is like a thing that like takes in an object and spits out another object of the right type, right? What we're saying is that like functions and implications are actually the same. In other words, when I say like, you know, we have an object A, right? And that if we now have a reflexive property that says like, cool, A equals A, right? That is a function. That's a function that takes in an object of type A and returns like a hypothesis with a constructed hypothesis that says A equals A, right? But that's exactly what implication is, like in standard logic, right? In standard logic, an implication is like that would be the same as saying like A is an object, and that implies that A equals A, right? So in Curry, this is like a first idea of like Curry-Howard, which is a function which takes in objects and builds other objects is exactly the same as an implication. Right, like these two things are like they play the same role. When you have a function that takes an object and gives you a hypothesis, that's the same thing as saying you have an implication that takes some objects with some types, which are themselves hypotheses, and then spits out a new object, which is a new hypothesis of a new type that you know is good. Okay, so that's part one. We'll start with that. Actually, it's just like, I think this is probably enough talking because it's actually very like, you know, this is very like up in the air for now. Let's be super concrete about what we mean at all times here. And let's hopefully we can use this to prove something like 1 + 1 = 2 if I have the time. I do have to head out in about an hour and a half to 2 hours, but okay. Let's get started. So what are we going to do? We're going to start with kind of this idea that like hypotheses are types. So a statement is a type. So before that, we're going to have, first of all, like just very quickly, a quick Julia review is we have, in Julia, you have abstract types and you have structs. So an abstract type is simply just like a type that other things can be part of. So one example of this is a floating point is a type of a real number. So if we say, we have real is a type here, right? And, float 64 is indeed a type of real number, right? So this operator tells you whether something is a subtype of another. Of course, a real is itself subtype of a real. But for example, complex is not a subtype of real. Oops. Simply because like these two things don't make sense. On the other hand, I do believe that this is true. Actually, it is not true. So a real is not a type of complex number because they're kind of like different. Okay. Of course, an int is also a type of real number, which is cool. And so anyway, so the point is, we're going to build this like hierarchy of types, some of which will be statements, some of which will be numbers, and some of which will be kind of some weird third thing. And in doing so, what we're going to do is we're going to essentially use Julia as a like mini DSL to like bootstrap a theorem proving system. So what we're going to do is we're going to build into the types of Julia itself, we're going to build in a proving system such that when a statement compiles, right, then that necessarily means that statement is a proof of the hypothesis, and that hypothesis must have a proof associated with it. In other words, the hypothesis is like correct. How we're going to do it essentially is we're just going to like use the Julia types and the fact that the Julia has like this nice hierarchy of types and whether things belong in it or not to construct fairly complicated types which themselves will encode theorems. And in doing so, you can essentially say, cool, if I can use the types that I have to build other types, then those new types are themselves correct, right? In the sense that like these hypotheses have a constructor associated with them, which means that this statement must have been true in the first place. Okay, enough blabbering. Let's start. So first of all, I'm just going to construct an abstract type, which is going to be just a type ty. And this is going to be everything in our universe that matters, so like natural numbers, propositions, etc., are going to be of this type, ty. Another thing that's very useful is to construct these things called terms. Oh, nice. It already got it. These terms are going to be concrete objects. So, a natural number might be of type, but a specific natural number that we pick, like 2, should be a term, right? And the idea is you can't claim equality between kind of objects of type unless they themselves are terms, right? So you can think of a term as a concrete instance of an object that actually we have some rules associated with. Okay, so now let's actually define, and finally, we have a type of term, and let's, also define a new type, which is going to be of type term, which we're going to call the proposition. And I'm just going to completely steal Lean's naming convention here, just so things are somewhat consistent. A proposition is going to be essentially a statement that we can make. For example, the statement 0 = 1 is going to be of type proposition. The idea is, the question now is like, why can't we make statements of the form 0 = 1? Is you can make statements, you can specify the type 0 = 1, but by construction, we will never be able to prove 0 = 1 using our proving system because there will never be a way for you to construct such a statement. or at least there shouldn't be, although we don't know that in Peano arithmetic, but whatever. Okay. Cool. So what do we have? We have an abstract type ty. We have an abstract type term, which takes in a new value, which is type ty. So for example, we'll see an example of this will be like a term, which is of type natural. And then we'll have an abstract type called prop, which is just going to be a proposition. So one natural notion of proposition is a proposition of equality, where we are making a statement that two things are equal. So to do that, let's say we have the equality, and we're going to have a term of type ty, right? And then we're going to have two statements. So it's proposition P, or let's say the left-hand side, which is going to be a term of type t, and the right-hand side, which is going to be a term of type t. Oh yeah, look at that, wow. It already has pretty much everything we need here. So, okay, so what does this mean? Essentially, like equality is going to make a statement about two things of the same type, two terms of the same subtype being equal, which is going to be t. So t is going to be the like type of the thing that is a term of. So one example is a natural number. So t might be a natural number. Left is going to be of type term t, right? Namely, the left is going to be like a thing which has a certain type, which is, in other words, a term of type t, and the same thing with right, right? And this struct, so the type, ec, whatever this thing is going to express a statement of the form the left-hand side equals the right-hand side. So that's neat and super cool. The problem is, like, we can't do anything with this equality, right? Like, right now we have no way of operating on this system, so to speak. So while we can specify there's a statement that two things are equal, like, that doesn't actually mean anything yet because we haven't specified what we can do with an equality. So let's talk about what we can do with an equality very quickly. So REFL, again, using the lean type, is going to say, okay, cool, let's take a term, any term of type t. And what that means is that, so this will be a rule that essentially encapsulates the following statement. If I have a thing of type t, then REFL should give me a statement that says t is equal to itself. So that'll be pretty easy to do here, and it's just going to be t comma t, right? So in other words, this REFL, if I have a term of type t, a thing that's constructed of type t, is going to construct a statement of the form t equals itself, right? And here, essentially, like, let's carefully trace the types. So we don't even actually technically need this, but whatever. So t is an object whose type is term t, right? And so again, this t here matches this t here. And then this thing is a term, right? So the left-hand side obviously matches the right-hand side as expected in terms of types. And so this rule expresses that something is always equal to itself. So let's export that. REFL. Okay, another thing that it is like super cool, which is, equality is symmetric. So let's call it sim. So, and we have an equality here. Let's see, so T, L, R. Cool. So here we should have, actually these should both be the same type. Anyway, okay. So essentially what we're saying is like, cool, okay. Another thing that equality lets us do is if we have, one side and the other side, right, we can take both. So we have A equals B, then B equals A, right? So we can replace A equals B with B equals A, and everything holds exactly as we expect. So all we're doing here is just flipping the left and right hand sides of this equality. And finally, we have trans, right? So we have two statements. So what is this? Trans tells you that if A equals B, right, and B equals C, and these things type check, which we will specify in a second, then necessarily it must be the case that A equals C, right? So let's write this in the standard way. So T, L, R, b2, and this is going to be equals TRS. Oh, nice. It already has this. So, okay. What have we done here? So here we've actually, like, this seems a little bit silly, but here we've actually restricted types. So we have terms that are of type T, right? And then we have the left-hand side is equal to the right-hand side. This is a claim that the left side and right-hand, this is a claim along with a proof, I guess, because we've constructed the object, that the left-hand side is equal to the right-hand side. Term 2 actually now states that the term, so the right-hand side of E1 must be the same type as the left-hand side of E2 for the statement to make sense. Right? So in other words, R here and left R here is, like, these two must be exactly the same type. What that means, essentially, like, this enforces a compile time check that says you can't take two arbitrary hypotheses and, like, you know, sandwich them in the middle. Like, it must be the case that, like, if A equals B and B equals C, that, like, you know, we could make it like A equals B1 and B2 equals C. Then must be the case that B1 and B2 are semantically equivalent. In other words, in our case, by definition, are using our types of hypotheses, they are equivalent to each other, so they are equal. Cool. And in doing so, now we have constructed this thing which says, cool, like, let's take the left-hand side of equation 1 and right-hand side of equation 2 and set them to be equal. And this is a new claim that we can construct starting with E1 and E2. Okay, so far, nothing super interesting. All we're doing is just encoding the standard rules of, like, logic directly in here. Okay. Finally, for fun, let's make a type. So, and let's call this ty. Let's call this net. And then now we're just going to construct a 0. So 0 is not going to be a type. It's going to be type terp net. Okay, and we're going to export 0. So let's see. I should be able to switch the environment. Ahaha. Here we go. All right. Okay. All right. So I already have a malformed expression, which is super exciting. Let's see. What does it tell me a term is a malformed expression? Okay, cool. So far so good. So what's the idea? Okay, cool. We have these types. We have this equality. We have this reflexive, symmetric, transitive. Okay, and now we have this 0. For now, it's not super important. But the cool part about 0 is that we can construct it. We can build a thing called 0, right? In other words, if we can construct an object, that object exists. And this, in other words, is the same thing as assuming that there exists such a thing as a 0. And we are exposing that to the user to be able to construct. Okay, so here is, like, what I mean when I say, like, a hypothesis is a type, and if you can build an object with that type, then that hypothesis must be true. So the statement 0 equals 0 it's not an obvious statement, actually, technically. I mean, it is in, like, general sense, but, like, from our type system, it's actually not completely obvious, because we actually have to, like, derive that from, you know, our rules that we have written. So obviously 0 equals 0, because by the reflexive equality, the reflexive notion of equality is, you know, we can take this thing and we can say, cool, like this is a true statement, right? Because again, you can think of functions as kind of the functions that we define here as the rules of the game. Like we are allowed to use these rules of the game, and we will later derive more rules of this game by kind of combining these initial things. But like that's what a proof is, right? Like a proof says, I take some standard set of rules, I like use those to derive more rules, and in doing so, I derive more theorems about the things that I care about, right? It's like the math is like made up by mathematicians to tell you more math, but in a type system. Okay, so what we've actually done here, like if you look carefully at this type here, down on the bottom right hand side, is we've actually proven that 0 equals 0. We have constructed an object which is of type equality that takes in a natural it takes in a type T, which is a natural object, and two terms of that type, and we've made the claim that 0 equals 0, which is like super cool and interesting, kind of, right? So this is now a statement, right? We've proven a statement that says this equality, we have an object of type equals 0, 0, right? Also, just for fun, let's actually make these slightly nicer to print. So function does not show. Let's make this print this equals this. Cool. So now it should be a little bit nicer. There we go. 0 equals 0. Okay. So that's the high-level idea so far, right? We have done very few things. So, I mean, another thing that's kind of interesting, of course, is we can apply symmetric to this, although it's a bit silly because 0 obviously equals 0. So now we can kind of start seeing like what it means to have axioms, right? What it means to have objects, which are things that we know exist, know, right? In some general sense of know. And what it means to have implications. So an implication is literally a function, right? So when I write REFL, right, that is a function which takes in an object and then returns a hypothesis with that object embedded in it that says like whatever that object equals itself. Let's actually start doing kind of slightly more interesting things. So another thing we can do is we're going to define our natural numbers as the Peano axioms. So let me actually pull those up because I like kind of remember them, but okay. So the Peano axioms tell you, cool, like, you know, equality is reflexive. We already have that. Equality is symmetric. We already have that too. And equality is transitive. This is a funny statement that I don't really care too much because whatever, we have types. So necessarily this is true. Like we can only make statements for which this is true. Okay. So now we're going to define this like thing, this successor function, right? So what we're going to do is it's kind of annoying because we don't want to define, you know, like a type of natural numbers for which like everything needs to be first defined and then we define the successor function. We're actually going to define the natural numbers using the successor function. So to do that, we're going to define struct of, you know, success. Oh, here you go. So what is this? Okay, this says cool. This suck is going to take a natural number, which is going to be your predecessor here, and it will construct a new natural number, which is going to be called the successor of that number, right? Let's also similar. I'm going to do sort of doing exports down here. It's a little bit cleaner. So, okay, so we have 0, right? That's a perfectly reasonable natural number. Another perfectly reasonable natural number is successor to 0. And we can see that that's fine. So this is a you know, one might think of as a kind of recursive type. So this is, of course, we're going to call this 1. So 1 is going to be equal to the definition of, by definition, successor of 0. Okay, because, you know, the next number after 0 in our integers is 1. Okay, similarly, we can define 2. 2 is the successor of 1, right? And so let's do it this way. I will declare these as types in a second, but for now, this will suffice. So if I do, you know, 2, so suck of this, oops. Let's do this right now. This is just as cool, like, you know, the successor of a successor of 0 is going to be some number, and that's going to be 2. Okay, so let's just define. So, okay, one thing that's important is Lean, of course, does this very nicely, which is it does not distinguish between types and things which inhabit those types, because by definition, there will only be one thing that inhabits that type, namely the proof that the type is correct, or that the type exists, and depending on where you stand on the constructive, non-constructive axioms, whether it's correct or not. Okay, but the point is, like, we're going to have to distinguish between types. So there's a thing of type 0, right? So 0 itself is like is a structure, right? So we see that this is a struct, right? If I do 0, on the other hand, it's going to be this is like a thing which is of type 0. Right, so this is a little bit annoying. We have to do this in Julia again because Julia is not like meant for this type of stuff. So whatever. But we can then construct things. So let's do a pretty printing here just to make this a little bit easier. Nice. So now when we write 0, this will actually be nice, and then we can write like suck of 0, and we have a succession function of 0. Okay, so one cool thing about this is, we can write things like, okay, 1 equals 1, or the successor of 0 equals the successor of 0. Cool. Not super interesting so far, but, we're getting somewhere. So with this, we now have kind of defined what the integers mostly mean. We are missing, other things. So we are missing, for example, this, which I will explain how we do that, and then this, which is a bit annoying. So we have 6 by construction, right? So every natural number, Sn is a natural number. How did we say Sn is a natural number? Well, we, by definition, say, cool, like every time you apply S, or the successor function, to any number, you're going to get another number, which is a term of type natural. Okay. So, cool. So hopefully we are like mostly making sense. I have no idea so far if anyone is. I guess we have Lucas on the chat, but okay. So now let's actually do something even more useful. Now we have defined the numbers, but we haven't defined anything that we can do with them. So that will require us to define addition. So let's define addition. We have here, so let's define this. So addition is defined in the following way. We say it is a function that maps 2 natural numbers, 2 elements of n, to another one. So the first axiom says, cool, like a plus 0 equals a. So that's the definition. So let's call that add 0, again in the Lean formal style. And what does add 0 do? Well, add 0 takes a number, in other words, a, which is of term nat, and says, cool, this is going to tell you, like, this thing tells you that a plus 0, okay, sorry, first, before we do this, we have to write this function. So let's define first a struct called add. Add is going to take 2 terms, each of type natural. Actually, let's even make this a little bit easier, which is going to call this nat term equals term nat, right? And then we're going to say, L is a nat term, R is a nat term, and then this is going to say, yep, cool. So, okay, so what is this? This is like a term that says, like, cool, we're adding 2 numbers, right? Like, this is, again, a statement that we are making. Like, when you say a plus b, that is not like a neutral thing. We are, like, making a claim about some object called a plus b. So we can encode that again in a type, which is going to say, cool, you have, like, a type that says you've added 2 things together, and that thing, when you add 2 things together, you have a left-hand side to that type and a right-hand side to that type. Okay. And so now we can define something like add 0. So what does add 0 mean? Add 0 is going to take a term. So it's a nat term. Actually, let's call this natural. So in this case, add takes a natural number, and returns a natural number, which is what this means. And add zero is the claim that indeed a plus 0 equals a. So what does that mean? That in written in our language here, it tells you if we add t to 0, which is our input, return nat term. Wait, what am I missing here? Wait, Kobe, what do you mean return nat term? So, okay, so we have add 0 here, right? So add 0 says like, cool, take a natural number, and that's a term. And that says, cool, every time you take, so we're going to define this as the axiom that says a plus 0 equals a. So what is a plus 0? Well, a plus 0 is a thing of type adding t and 0, right? So the left-hand side of this addition is t, and the right-hand side of this addition is 0. And we're constructing an object that says add. So there's a statement that we've made that says like these two things exist and we're adding them together. And add 0 is the claim, right, that says there's a claim that these two things are equal. So in other words, by like we've defined a like hypothesis that says when we add t and 0, we have a new type of object that claims the equality between t, the addition of t and 0, and t itself, right? So we can add that, and like let's pretty print this slightly nicely. Function base.show. God, I do love that this thing is so nice in this terms. So I'm going to remove this. This is going to be terrible for other reasons, but it's fine. Cool. And now we can do something that's like kind of cool. So let's say, so if we do add 0, for example, of 0. Oops, I need to export this thing. Then, of course, we now have the like cool new claim that says 0 plus 0 equals 0. Congratulations, right? So this is a claim, right? Like we've taken an object, namely 0, and we've added it to a 0, and then we get 0. But of course, we don't have to do that with just 0. We can do that with suck of 0 or 1. And this is now a claim, right? Like add 0 is the statement or this assumption we've made that says we're going to, add 0 to the successor of 0. And in doing so, we're going to get S0 again, right? And this is, again, a claim, right? So add 0 takes us a thing and then maps it to a claim that makes sense. Definition number 2, which we're going to care about in this case, is going to be add suck, is what I'm going to call it. Again, using the lean terminology, which says a plus the successor of b is going to be the same as the successor of a plus b. And so how do we do that? Well, we define let's take this as, a, which is going to be a natural, and then b is going to be a suck. It's going to be the equivalence between add a and b, and then suck add of a and b prime. Exactly. Wow, we love our robot friends. Okay, so what does this mean? Right, like add successor says, okay, cool, I'm going to take a, which is going to be any natural number, and b, which is needs to be by definition a successor, right? So b can't be like 0. Right, that's the same. This is the same thing as saying like this thing is successor of some previous thing, and this is going to now return the claim or the statement that like if we add a and this successor b, then necessarily what we're doing is we're taking a successor of adding a and b. Right, so I have no idea how this will turn out, but let's see. So 0, and then suck. 0. Oh, this is going to fail right now, actually, because I need to export this. Okay. Then exactly. We had exactly what we expect. Obviously, it's a little bit silly right now because we're kind of like taking a successor, but the point is, add suck tells you like, cool, so if you have an object that's any natural number, then you have a successor, which is any other thing. right, then adding that object plus a successor is the same thing as taking a successor of the addition of the two. And actually, this turns out to be enough to completely like define addition, which is kind of cool. So cool. So far so good. Let's see if I can't unsee the nat term now. Oh, I'm so sorry. Sorry, I meant to make it only one of these, but alas, natural seems to be just like a nicer version of using term nat. Okay, so I think this should be enough to prove that 1 + 1 = 2. I'm not 100% sure actually, but okay. So what is first is first? Let's just like write it all out. So what is 0? It's going to be, well, just that is the object of type 0, which we construct, and then 1 is going to be the successor of 0, right? So and then 2 is going to be the successor of 1. So okay, so we have 0, 1, and 2. I don't use 0 here just because it's a function, and that would be very annoying. So z it is. Okay, we would like to prove that 1 + 1 = 2, which seems like, again, we have a whole system now. Okay, so let's prove this, and then I'll take a step back and show what the hell we've done, like in just about 50 lines of code. Okay, so what is the statement? Like, we would like to prove, again, as before, here, I'm going to make a new... new folder, 1 + 1. Okay, so using interactive proving, we have z is 0, 1 = suc(z), 2 = suc(1), great. Okay, so first things first, what do we want to prove? We would like to prove the statement that 1 + 1 = 2. Okay, so in other words, we're going to prove this. If we unroll that, right, that's the same as saying, so, and for fun, actually, let's define these types. So let me just do this very quickly. I'm going to define types, which are 1 is going to be of type suc(0), and 2 is going to be of type suc(1). So 0, suc(1), 2. So now if we take 1, great, and 2, it's going to be suc(0). Great. So now we have like these types. So again, remember way back when I said a hypothesis or a statement is a type. Here is a very concrete definition of what that means. When we say 1 + 1 = 2, we're going to call that our goal. We're going to call it a goal type. And what we're saying is okay, we have equality, in other words, this thing, between the following types. So equality is a type itself, which takes in types. And this is going to be actually slightly annoying because we have this thing, but whatever. So the type is going to be saying, okay, equality between nat. So I'll explain why I have to preface these with interactive proving. This is natural. No. Okay, so we are expressing equality between the left term, which again is a term of some natural type, namely 1, and the right term, which is going to be a term of a different type. So specifically, we would like a type that says, cool, we have the following two things are equal, is 1 + 1, right, and 2, right? So this, again, like parsing this type, what it literally is saying is, if we can construct a thing of type equality, add 1, 1, 2, we have essentially constructed a proof that the left-hand side and the right-hand side are equal, given our assumptions about how addition, the natural numbers, and equality behave, right? So again, let's run these things, and then we have a type. So our goal is now to construct an object of this type using the rules that we have available to us. which are namely add 0, add suck, reflect, symmetric, and trans. Cool. Okay, so you'll notice first that like I can't add arbitrary things together. Like I can only make statements about these that are like essentially these forms, right? So first off, let's unpack the definition. We have, I might actually need one more thing here, which is a little bit annoying, but let's start with this. So add suck, again, we'll take a successor function. So in this case, we'll take 1 and 1, and we'll output a proof or a hypothesis along with an associated proof that says like, we can move the successor function for the right-hand term to like the whole term. Right. So specifically, right, what we can see is the cool part about Julia, of course, is that it has a REPL, so I can actually like when I write these things and run them, it just automatically gives me the type and constructs the object. So specifically, we have like almost everything we need here, which is rather funny, right? We have this S0 plus S0, right, equals S of S0 plus 0. This is almost all of the way to proving that, 1 plus 1 equals 2, right? Because S of S0 is 2. The problem is now we have S0 plus 0, right? And we need to like actually define or like move around what that means, right? So, okay. Actually, I do think we need one more thing for equality, which is apply function. So let's make sure. Yes, okay. So, okay, last but not least, we're going to define one more thing, which is if I have a function and I apply it to both sides of an equality, the equality remains true, right? This is just another definition of like what it means to apply a function. Okay, this is just, it might make my life a little bit easier, so I will do it anyways. Okay, so now we have like, again, like because we can construct this thing, we now have this tells us that the following statement is true: S0 plus S0 equals S0 plus 0. So let's call that step. Let's call this add 1 ec add ec suck add 0 or something. It's a bit of a verbose name, but whatever. We already have add 0 right here, but yes, we should use that exactly. So, okay, so cool. Now we have like, okay, we somehow now need to show that S0 plus 0, right, like equals the thing we want, namely S0. But what's that? Well, okay, 1 plus 0 ec 1 is, of course, exactly the hypothesis we want, which is namely, please apply S0 plus 0 equals S0 to this. Right, so now, like Kobe was saying, we need add 0. So now we have what's inside of this thing, right, on the right-hand side, and what's on the left of this thing on the left-hand side. So we can almost, like so close, apply this transitivity of equality. The problem, of course, is that we can't just apply it willy-nilly to the inside of this, right? Because again, this is like, we can't apply transitivity directly because this whole thing is encapsulated inside one more S. So lucky for us, I have just like, added this nice thing that says, 1 or suck 1 plus, and then I'm going to say apply function of suck, right? So again, this apply function says it is true that if I have a claim that the left-hand side equals the right-hand side for this thing, then necessarily applying a function to the left-hand side and the right-hand side also maintains that equality, right? In reality, we should type check this to make sure the types returned by the function are all correct or whatever, but this is actually, these should be identical. Okay, and finally, so with that statement, we now get this, I need to do this. Sorry, I need to actually call it constructor. I don't need to call it type. So with that, we say, okay, cool. We started with our claim that S0 plus 0 equals S0. right? And now to, of course, like again, these two things, it's a claim that we know is true. So now we can, to both sides, apply the successor function that says, okay, s of s0 plus 0 equals s of s0, right? Like all we're doing is applying the successor constructor to both sides of this equation right here. And in doing so, we now have the left-hand side here matches exactly the right-hand side of this. So, you know, guess how we can finish them off? Well, we can apply the transitivity, right? So, you know, final goal is going to be apply the transitive function of the trans, right? That says, cool, if we take an equality for which the right-hand side equals the equality for a different, or equals the left-hand side of a different equality, then we can put both of those things together, right? And with that, the final type is s0 plus s0 equals s of s0. And how do we check that it's good? Well, final goal, by, like we've said, a statement is true if we can construct an object of that type. And indeed, we have just constructed an object of that type. Therefore, that statement is true. So, okay. We've gone like a million miles an hour. We can now like go all the way back, take a whole step back all the way to the beginning, which is what the hell have we done, right? Like yeah, we proved 1 plus 1 equals 2. That's like super sick and cool. Yeah, we did it in like whatever, you know, 60 lines of code or something, super sick and cool. But like, what the fuck does this all mean? So, okay. Remember at the beginning I said, so these are all examples of what's called the Curry-Howard correspondence, right? Which is this idea that like functions are implications, right? And that hypotheses are types. So when we say a hypothesis is a type, I do mean that in a very strict sense, that like a hypothesis, in other words, the hypothesis that 1 plus 1 equals 2, is a type that is of type equals, you know, type add 1 comma 1 and the type 2. And these things themselves unroll back to each of the like original axioms, right? So 2, how did we define 2? Well, 2 is defined as successor of 1, right? So it is the 2 is the type whose you know, which is the successor of the type 1. And then 1, of course, is itself recursively defined as the type which is the successor of 0. Right? And 0 in our case is simply like a statement, a thing that we have made. Right? So when we write something like struct 0 and we build 0, this is using the assumption that we can build an object which is of type 0. Right? And of course, now that we have the 0 object, we can of course build objects which are successors of 0 by definition, by our definition of successor, right? The successor simply takes a predecessor, which is any natural number, right, or any term natural number, and then in doing so constructs a new type around it that is like the newer number that we get, right? And so that's what these mean. Like these are actually like literally objects of the type, you know, 0, 1, capital 2, right? And in constructing them, we have said that they exist, right? And again, this is an assumption, right? Like this, the fact that we can construct these things is the assumption that we've inbuilt into this because we've said like, user, you are free to build a thing of type 0, and user, you are free to build a thing of type suck. Okay, so now the question is like, user, you are not free to build a type of type equality, you know, nat 1 add 1 2. Right? Like the only ways you can build these things, these types, is by following these rules which we have set out for the user, namely the fact that equality is reflexive, the fact that it is symmetric, the fact that it is transitive, and the fact that for any given equality we can apply a function to both sides of the equation, right? Those are the only ways by which the user can interact with this like type equality, right? So this is what we mean when we say like you can like only when you build it is like this thing is sound, is because by our construction, like the user cannot access the constructor for equality except insofar as it can do so by following these like these rules that we have set out for them, right? And these rules are functions. They like take in a hypothesis, or they take in an equality, or they take in a term, and then spit out a like statement of a given form. But that statement, what is that statement? Well, it is a type, right? And that type actually has is a thing that's constructed of that type, which in other words is a hypothesis that we have fulfilled, like whose construction we have fulfilled. So that's what we mean when we say like, cool, like proofs are things that are built out of like individual steps, right? And those individual steps are the axioms. In other words, the things that either we have set out for the user or we have proven based on these axioms. So one example, like what I mean, well, I'll show what I mean when I say this. You could think of as a lemma. A lemma itself is also a function, which takes in hypotheses and spits out a new hypothesis that is the like output result. And in doing so, right, we can be sure that so long as we know that the types that we've constructed here and the function that we constructed here actually don't expose anything that is unsound to the user, we know that the user, once they've applied all these transformations, must have constructed a correct proof of the final statement. So, this is, again, pretty silly to prove that 1 + 1 = 2 and do all this work to do so, but the idea here is like fairly clean, right? Like, we start with only the things that we are given, namely the definition of addition, which is that something plus 0 equals that, and then the successor function, the addition of a thing and the successor is the successor of this, sum or whatever, right? And in doing so, we have received kind of this nice final structure that gives us everything we need to know. So long as so long as this small kernel of things that we know is correct, then we know that every proof that derives from it must also be correct. Assuming Julia's type system is sound and all this stuff, obviously, like we're building off the fact that Julia itself has like a sound type system. But in doing so, we have all the things that we need. Okay. So you might say this is cool, Guillermo, but like, well, where are our lemmas? Right now we've proven a concrete claim that 1 + 1 = 2, right? But what about general claims, right? What about the claim like, n + 1 is a successor of n? And funnily enough, these things just kind of come for free. So from this construct of a type system. So let's do something interesting, which is going to be this function. This is actually just going to be a generalization of this proof in the case for arbitrary n. So here n, and this is going to be true for all n, and we're just ignoring our term, not true. Okay. Cool. So what does this mean? Like, what is it? I need, like the first thing that you should ask when like you write something like this. It's clear what this means now, right? Like when we say 1 + 1 = 2. What that actually like explicitly means is, again, it's a type that says, okay, when you like interpret all of the like individual types and roll them out, we actually get indeed that 1 + 1 = 2, and we get a type of that form. And proving this statement, in other words, proving that this type is inhabited or there exists a thing, is the same as kind of like applying a bunch of functions and constructing a object which is of this type. But what does it mean when you have kind of like a universal quantifier? Right? Like, what does it mean to say this thing is true for all n? Right? And if you like turn your head a little bit, what this means is that we have a function, right, which takes in any natural number and spits out a proof that that natural number plus 1 equals the successor of that natural number, right? So in other words, like universally quantified statements are actually themselves are just simply functions which take the universal quantifiers and spit out a new proof and spit out a proof that the goal is true for this like for any number, right? So in other words, we will see like we will actually use Julia's type system to type check that this is true. In other words, like if we start with any number, the function itself type checks to actually spit out a function, a number of that is always a successor. Okay, so again, let's make this another concrete thing. So we can do this again. Attractive. Cool. Oh, nice. Look at that. All right. This is gonna be net. And this is also gonna be net. We don't need this. Cool. Okay. So what is this? Let's write this all again. Nice. Okay. So what is our goal type? Actually, this is not right. Okay. So our goal type now is a funny thing. Our goal type says, okay, sure, we have a thing of type nat, right? Which, whatever, doesn't matter too much. What we're saying is we have so n here is just like an arbitrary type. We don't know what the type is. We have no idea what the type is because technically, like, the prover or the, like, proof system can input any type it wants into here so long as it, you know, accepts all the constraints, right? Like, you can only add natural numbers by our definition here, so it has to be of type nat. But okay, and what we're saying is cool. Like, what is our goal type? Our goal type is that for any n, we should be, like, whatever that type is, the following should be true. The addition of that type plus 1 must itself equal the successor of that type. Right? So you should see something very similar to what happens here, which is like, you know, we are postulating that adding 1 and 1 equals 2. Right? Here we're postulating that adding some type and the type 1 equals the successor of n, where n. Right? So now our goal will be to construct a function whose output result, whose input is always, you know, so let's just say add 1 or whatever, will always be a natural number. So let's write that. And whose output will always be a concrete representation of goal type. So we can write this as goal type. Right, and this ensures that, like, our return value must be of type goal type. Of course, I mean, like, you know, as you can tell, even the AI is not this dumb. It knows very quickly that the proof style is essentially exactly the same one as the one we have here. Right. So, essentially, okay, what is the goal type? Well, look, we're taking an n, which is an actual fixed number that we care about. And what are we going to do? Well, we're going to, like, add suck to n comma 1, right? So this n is now not just the successor of 0, but it could be any n whatsoever. Similarly, we're going to prove that the successor of this thing plus 0 is exactly what you expect, right? So this is going to be, so let's write this all out, is n plus 1 equals, there we go, wow, that even knows what to do. Right. Similarly, right, or equivalently, let's write this as s of 0, right? We of course know that adding 0 to both sides doesn't change anything, so n 0 is n, right? And then finally, we have that s if we are just applying s to both sides, right? So it gives us this, right? And then finally, you know, this thing and this thing are exactly the same. And so we can just apply our transitive equality to get this. That's not right. To get exactly what we need. And indeed, we just return final goal. So what's interesting is the fact that this compiles is enough. Oops. So the fact that this compiles actually automatically proves the claim for all n. Right? Because again, we've started with a natural number. It's a concrete natural number. We've applied only the rules that we were given. And then we return a thing of a given type. But that type is always a correct type. So for any possible n, right, the return type of this function is always the correct type, which immediately implies that this statement must not only be true for 1, but indeed must be true for any n. For fun, we can do this thing of, like, we can just run add 1 on just the number 1, and of course we recover our original claim, which is right up here, just final goal, right? So final goal equality here, of course, is simply the claim that 1 plus 1 equals 2, and then, but that is exactly the case of what happens when we apply this function to only 1, to the number 1. We can also apply it, though, of course, to 2, though. That's totally good, right? Oh no. Let's see. What have I screwed up here? And suck n. All right, where'd you go? let's see. Technically don't really do this because we just return this, but let's see. Technically, you know, if everything was nice and sound, this would be a non-issue, but what am I missing here? So we have, okay, yeah, so you can see that like unrolling these things is kind of a huge pain in the ass because we now have these like back things, but add n is equal to suck n. Yes, so far so good, where n. Wait, what is this type? All right, let's see. So we add, cool, s of 0 plus s of 0 is s of 0 plus 0. Great. Should be able to add 0 plus n. So it should be s of 0, 0 plus 0. Great. Oh, we don't get suck n plus, I see. N plus 0, wait, apply function. Did I fuck up the type here? Let's see. So we do get this, which is good. And then finally, we should get this. Got it. So let's try this. Just return this for now. Okay, so what do we have? We have s of s0 plus s0 equals s of s0. So far, so good. What is this type? We should be able to add n and 1, and it should be the successor of n. Right? So let's see. So this seems like the right type, right? This is, it says 2 plus 1 equals 3, right? Which is what we're saying. Our claim is the 2 plus 1 is the successor of 2, right? Equivalently. Also, ideally, this thing, if this function compiles, it should automatically be the right type, which is why I'm a little bit confused by this, but that's fine. Let's see. How do we deal with this annoying thing? So what do we have? We have nat. If we add the successor of 0 to the successor of 0, we have the successor of the successor of 0. Right. So, oh. So we have there. Suck of 0. And suck of 0 equals suck of, yeah. is going on here? Let's see. Am I missing something silly here? Wait, what the hell? Am I just dumb? What? Oh, okay. Wait, what was wrong with this? I'm so confused. What? Okay, I have no idea what the hell's wrong here, but whatever. Wait. Okay, let's do this. Yeah, okay. I have no idea what the hell's wrong here. Okay, well, whatever. Anyways, looks like for some reason it was right, but I don't know why. Anyways, we can also do, of course, because if it compiled, it should have been correct automatically. So that's why I was confused. So is a full type. Is a full type. Anyways, all right, whatever. So, okay, anyways, so TLDR, I have no idea what the hell I changed, but TLDR is we're good, right? So, as before, if we have a function that takes in a natural type and always can convert the natural type to a goal type, then necessarily we have constructed a function whose that proves that this is true for all natural numbers, right? Like that's the definition of something being true for all natural numbers is you give me any natural number, I can always give you a type that type checks, and I can do that by any transformation of like specific types to other types. So this also shows the construction of like why this is so much more natural than like the very initial idea I was talking about, where it's like you can think of proofs or statements as strings and then you apply formal rules of reasoning to them, right? Is because things like universal quantification over like a formal string is a very annoying thing to define, right? Like you have like, what is it like when you have a for all n is true, whatever, right? You now have to define like a bunch of statements about what for all means, but like we know what that is naturally, right? Like if we say for all n something is true, right? For all n hypothesis holds, that is literally saying, please, for any n of this type that you give me, I can always construct a proof that is of a certain type, right? I can always construct an object that is of type hypothesis, right? In other words, if that function type checks such that like for any given type the output type is always correct, then necessarily it must be the case that that function that is true for any function, for any value, right? And so what we're saying when we say a function, what's interesting is like a function is an implication, but a function that takes a free variable is not just an implication, it is a statement about like over all possible things of that type. Yeah, so anyways, as expected, right? So we could let's call this goal type 1 just to be even more particular about this. Actually, I'm going to do this. Goal type 1 equals goal type. So say this is true, this is true. Okay. Not only is it a type goal type, but it's a type goal type 1. And this is true too. What's cool too is actually goal type 1 we know is a type goal type, right? So it's also true, right? So this is another very interesting observation about universal quantification that we have from subtypes is a statement that is like strictly stronger than another in many cases, right? Especially when it's like this clear, it's like very strictly a subtype of a different type. Right, so goal type here is a universally quantified statement that says for any n this is true. Goal type 1, defined here, which is just says that specifically for the case of 1 it is true, right? And it's exactly as you expect. A subtype, a goal type 1 has subtype of goal type, right? Because of course, right? There's like this is the special case for n equals 1, and so you also get that for free. Okay, so far I haven't, this is like kind of a crazy thing, right? Like we've essentially leveraged Julius type system to construct a interactive proving system, right? Or interactive, what do we call it? Interactive theorem prover, right? Where you can take all of these things, put them together, and if the types check, then everything is good. And we haven't actually used any, like, there's no metaprogramming or anything. All we've done is, like, all sorts of silliness. I'm going to explain why Julia is probably not the best for doing this, at least not without metaprogramming, although I'm sure you could, which is constructing false statements. So Julia's type system is powerful enough to incorporate all of this stuff, but here is like one very annoying thing. Fake goal. Yeah, I could do 1 + 1 = SFN, but unfortunately, I do not want to prove the fact that addition is commutative. Actually, it just suffices to prove that 0 + n. No, and then you have to prove that addition is commutative, which is actually very annoying. But yes, exactly. So multiple reasons why Julia is not the best language at this, unless you like want to get into metaprogramming. But number one is you can actually construct false statements fairly easily, and that's actually not like a, necessarily a bad thing in this general sense. It is just a little bit annoying. So let's say, we would just want to make the statement that 1 and 1 is 0, right? As I've said before, we can construct statements, right? Like if you can construct a statement, then the statement must be true. The problem is that Julia, by definition, does not have private members or private constructors. So technically, if the user were to be a little cheeky, you could construct a very lovely false statement by simply instantiating the constructor for equality, right? Which says goal false, haha, right? Oops. And then we can, actually, let's see, then, 1, 0, right? By just plugging in the right types. 1, 0. Correct, exactly. Once you have a false statement, everything is provable, right? So now we have constructed an annoying type that says, cool, s of 0 = 0. So the problem, of course, with Julia as it stands today, if you don't want to do this inside of a macro block where you actually check that constructors that are not public shouldn't be called, is that constructors are exposed to users by default. So anyway, so you have to be a little bit careful here when you write things like this. This is because constructors are public in Julia. To make sure that like somebody isn't, accidentally constructing the type. Of course, there's a reason why I didn't expose the EC type here, and it's because in order for you to do this, you actually actively have to call the EC type, right? You have to construct this specific type, and then once you have the correct type, you can of course construct any object that satisfies the type constraints, right? But anyways, okay. So now let's actually do proving something isn't true. So to prove something isn't true, we're going to prove that 0 actually doesn't equal 1. And we're going to use exactly the trick that we just used to construct a fake false statement. Okay, so what does it mean to prove that something isn't true in this like weird setting? To prove that something isn't true, it means that we have a hypothesis that implies false. So false is a type, which is never constructible. So we're going to call this a struct false. Just maybe a prop. And there's a bunch of weird notifications. I have no idea. So okay. So false is a proposition, right? It should never be constructible. So in particular, I'm never going to expose false to the user. Again, Julia always exposes stuff by kind of name spacing. There's no notion of private in Julia except insofar as you're just not actively accessing it. And then we're going to actually use the Peano axioms here to prove that something is not true. So the last Peano axiom says for every natural number n, s of n = 0 is false. That is, there is no natural number whose successor is 0. So we're going to write that as before, right? Like these are axioms that we can state. So we're going to write that as suck any0, right? And this is going to take any successor, and it's going to say that this is false. So any successor, and this is not going to be, wow, this is just totally wrong. So successor n equals 0 is going to take an equality. So let's call this t, which is going to be an equality of not suck n and 0 exactly, where n equals false. So it's going to say, okay, cool. Like, look, man, you give me anything, any statement whose type is I have an equality between a successor of some number and 0, and that's always going to return false, right? So we can export this one, of course. And then, in reality, we should probably put this up with the suck, especially the add here. So let's put this up here. Okay. And then let's export this here. So this is what it means for, okay, so we have suck no 0, and specifically if we do something like, we have our cool little equality, which is called haha. Oops. Right, then out comes a thing that says false. Like this thing just isn't true. Right. So to prove something isn't true, what it means is that we're going to assume something, the statement that we want to prove is false, and then prove false from it. Right. This is like, the idea is you've kind of derived a contradiction by starting with the hypothesis and then moved all the way down to proving that false is false. So this is the definition of saying a statement is not true in constructive arithmetic, in constructive mathematics. So in our case, let's not do this dumb thing. So let's prove something isn't true. Let's say bad assumption. So another reason why you would want to actually have this is true or false. Z, just the same thing as up here. So we are going to assume the statement that we want to prove is false, right? So in this case, that 1 is indeed not equal to 0. And we're going to use, of course, our cheater method here that we've just constructed, which is the axiom that says for every natural number n, Sn equals 0 is false to prove false, right? So that assumption, and then our goal type is going to be equal to interactive proving not false. So our bad assumption here is going to be cool. We've taken this thing, and what is the type of our bad assumption? Well, our type of bad assumption is exactly what we expect. So let's do type of. Let's actually make this. So their bad assumption is an object which has type the successor of 0 equals 0, right? Just from down here on the bottom right. And so, but we know, again, by our construction that necessarily anything that equals 0 is always returns false. Like this is just like a false statement. Like this takes in any hypothesis which says successor of n equals 0 and immediately outputs false. And in so doing, we can now, of course, just do suck n equals 0, bad assumption is a goal type. So in other words, this thing is false, and that returns true. Right? So that's how you prove that something cannot be true. I don't have principle of explosion here, so and we'd actually have to incorporate the fact that, false actually gives you anything. It's very useful for actually proving things that are not true. So, but for now, like this is good enough. Okay, so assume false statement, then prove false. So cool. Okay. I don't know. Are there any last questions? I think this is probably getting to near the end for me to keep on blabbering on about this stuff, but let's see. What else can we do? We could do induction, I guess. So the cool part about also Howard Curry in languages like this is that you don't need to define induction at all. Induction is something that comes for free because, again, a function, right? Like you can think about this thing as like being an automated kind of mathematician, and induction essentially means like I have a procedure to construct for any number n, given the ability to construct the next number. I can construct a kind of chain of statements that imply that the last thing, I make a claim about 5, right? But induction essentially says I can construct a chain of statements starting from 0 to 1 or something that implies the next statement is true for the next kind of ladder rung, right? But that's a procedure. That's not an assumption. So induction in our case actually is simply like a combination of a bunch of basic tactics. So maybe let's do that. So let's do doing induction. So let's see, let's call it function induction. So we're going to take base case, which is t, and then we're going to take successor function, or let's call this what do we call this? U. Oh, thanks, Bolton. Yeah, hopefully it's been a little bit fun. I don't know if I'm going to be able to finish this in time, but we'll see. So I do have to head out in a little bit. But so what do we want for recursion? We have a base case, which is the hypothesis that we would like to prove, right? And then we have a recursive step, which is a function. That function should return a type, which is a hypothesis of the next number. So the problem is there's no type constraints for functions. So in reality, the way to do it is like to construct a struct which keeps the types in Julia and then checks that like whenever you apply a function that the function compiles to the right types, but it's kind of a little bit annoying, so I won't do that. Let's see, maybe I'll do induction in a separate video or something of the like, because I think I'm starting to get a little fried of like speaking to a random computer, but cool. Actually, let's keep it as this right now. So I'll put this up as a little repo thing at some point, or some like GitHub gist or something of the like. But that's the TLDR. I mean, like, look, we started with a small kernel of about 61 lines of code with plenty of white space in the middle, and out of it we could prove things like n+1 equals s of n using just Julia's type system. So all I've done is kind of like lift Julia's type system to construct these objects, which themselves are, statements and proofs and all this stuff. And hopefully this makes a little bit of sense, like how the Curry-Howard correspondence actually works, like what that means. Right, like when we say like a thing is a type, we do literally mean like, again, Julia is not a system that's made for proving this kind of stuff. It's literally just a general, system that happens to have nice types, and like that is enough. If the types are rich enough, it's enough to like kind of construct these Curry-Howard correspondences and embed this whole system inside of it, and therefore like construct an entire interactive proof system that makes sense. Not just that, but also kind of secondarily, it doesn't take very much, right? Like all it takes is you have the ability to kind of construct these constrained types, right, that we have here. In doing so, you can build certain functions which tell you what you can and cannot do, what are the rules of the game, and you get to like apply those rules as you wish to kind of prove other statements. But again, statements are simply like, do you have an object of that type? Right, so a statement is true if there exists an object of the type, and that you can only do that, construct those things, if you're following the rules of the game, which are given to you by this kernel, right? And so long as you agree that, first of all, Julia's type system is sound, but which is honestly the bigger one, and then number two is that this, the small kernel of whatever 61 lines of code is correct and constrains things the right way, which is pretty easy because it's very short, then necessarily for free that like the output of anything here is correct, right? So again, so long as the user doesn't cheat here, but you could guarantee that if you use metaprogramming, you could use Julia's metaprogramming facilities to ensure that like the user can never construct things that it doesn't have access to. So while it could state such types as this, the user could not construct this object directly, just because that would be kind of outside of the kernel, the proving kernel. So yeah, you could also do things here, right? Like here we have to assume a bad assumption. You could also do that within metaprogramming. So if you're trying to prove false, then you allow the user to assume a bad assumption, all sorts of stuff. But the point is like, it's not that complicated, right? Like this is like a very, 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 very stripped down version of Lean, but this is essentially what Lean does. Lean does exactly this type of stuff. It has exactly this type of type checking. Of course, it embeds with things like satisfiability modular theories to be able to do things like tactics. So when you prove, 2 + 2 = 4, you don't actually have to go through this long proof where you carefully unwrap all these things. You could say something like by ring. And Lean is smart enough to figure out that it has these techniques that it can use to just like reduce this down to an obvious statement, and in so doing, you prove some final result. Not just that, but like you could imagine also doing the same thing within here, or Julia, or again any system which has strong enough types. So you could construct also similarly a minimal kernel with proofs inside of Rust. Rust has a perfectly fine type system. And you can imagine using the LSP itself, which will tell you the different types of different things and whether different things compile or not, automatically as ensuring whether the given types are correct. And so what's cool is like, hopefully this also gives you a flavor for like why type systems are proofs, right? Like if a type system checks out, in other words, if like in Rust a program compiles, you have by construction guaranteed certain things about the program's execution, right? And similarly, right, like and specifically, the types and the functions mapping different types are themselves a proof that is true, right? Like these are all proofs that are kind of like floating around in ether, and these are all kind of equivalent. What's cool, of course, is like for a strong enough type system, not only is it true that you're proving like certain things about the execution of your program, but you're also kind of conversely can prove things about kind of arbitrary systems, right? Like here we embedded piano arithmetics directly within the type system of Julia, but that's, one small thing. You could actually kind of embed pretty strong arbitrary type systems. For those in the know, like there's this thing called like the ladder of types, but in Julia you could do things like type, ty, and that could be your ladder of types would be type of, something like that. Right, I haven't seen anyone try this. It's a bit silly to do, of course, but like you could imagine doing like your ladder of types is like actually like these wrappers, which you then can deconstruct and all of this stuff. And so in some sense, you could kind of like rebuild Lean inside of the Julia type system, I suspect also inside of the Rust type system. Of course, again, these languages are not made for this, so you'd have to like retrofit it this way. But the point is that Lean is not a complicated thing. It's actually a very beautiful, clean, simple thing that uses these types in these very nice ways to be able to prove abstract statements. And this is, to me, was very, very informative in understanding how all this stuff works and like why we can do the things we can do. So cool. I think that'll be it for me. If there are no more last minute questions, ideas, notions, constructions, vibes, I think I will probably sign off and get back to doing some amount of real work. I think unfortunately there is a bit of a delay between these two things, so I'll wait 1 minute. Cool. Alrighty, well, with that, I think that will be it for me. Let's see if I can figure out how to, end this bad boy. But cool. Thank you all for everybody who joined, and yeah, enjoy your rest of your day.